Okay, so screen is visible now.
Yes, sir. Listen, sir.
Okay, fine. Okay, so yesterday we have done up to Woodward's reagent. Okay, today we will start. So today we have Prevost. Okay, Prevost reagent. So yeah, Prevost reagent. So first of all, what is Prevost reagent? So this is your silver acetate. Okay, silver acetate in presence of iodine. Okay, silver acetate in presence of iodine. So suppose you have this alkene compounds. Okay, if I have iodine, so what will happen? So iodination will happen. The alkene will attack on this iodine. This iodide will leave from here, and this iodine has also what? Iodine has also lone pair. So now iodine will attack through the lone pair. So what I am getting? I am getting this three-membered cyclic iodinium compound. Similar mechanism. Okay. Now next step is what? You have silver acetate. So silver acetate means what? Ag plus OAC minus. So OAC minus will attack here. This bond will break. Okay. So that means what? OAC is attacking from below the plane. So I have here OCOCH3, and above the plane I have iodine. Okay, now this oxygen has lone pair also. So what will happen? This oxygen will attack through the lone pair. This iodine will leave. Okay, from which side it will attack?
Below, sir.
Below the plane.
Below the place.
Below the plane, correct. So it will attack from below the plane. So I have what here? CH3. Here also I have double bond O below the plane. So this is getting positive charge. Now what is the difference between your Woodward reagent and this Prevost reagent? So Prevost reagent we are not using water. Okay, if you see in Woodward reagent, what we are using? We are using this water. Okay, water is present here, but in Prevost reagent water is absent. So that is the only difference. And if water is absent, so that means again, what is the nucleophile you have? So again OAC minus is the nucleophile. So now OAC minus will attack on this carbon, and this oxygen is positively charged, so this bond will break, and ultimately this oxygen is getting neutralized. Okay, so what I am getting? So here I have oxygen, then what? C double bond O CH3, and it is attacking from opposite face. So opposite face means what? Above the plane. Above the plane. So below the plane you have this group, and it is attacking from the opposite face. So that means above the plane you are getting this OCOCH3. Now if you do hydrolysis, so this is not part of the reagent. Hydrolysis is different step. Okay, so hydrolysis means definitely water is coming. If you do hydrolysis of ester, what will get? Hydrolysis of ester, what you will get? You will get alcohol. Okay, how? So suppose water is there. Okay, so water is attacking on this carbonyl carbon. What will happen? This bond will break. Again this will come back. Ultimately this bond is breaking. Carbon oxygen bond is breaking. Similarly here also, if water attacks here, this bond will break. This will again come back, and ultimately this bond is breaking. So you are getting this diol compound. Clear?
Yes, sir. Yes, sir.
Clear, right? Fine. So this is basically your Prevost reagent. Okay. So now suppose you have this compound cyclohexene. Okay. So here I am giving two reagents. So number one I am using here silver acetate in presence of iodine. Okay. And number two is what? H3O plus. Okay. This is which reagent? This is your Prevost reagent. Okay. And if you use like write down like this, they will give like this. Okay, same reagent they are mentioning water, so that means this is your Woodward reagent. So number two is your hydrolysis step. Okay, and here water is giving with the reagent silver acetate iodine, so that means it is what? This is your uh, Woodward reagent. Now tell me the product. Tell me the product.
Well,
Hmm.
the both will have diols will have products.
Diol, but the thing is, what about the stereochemistry?
Sir,
What will be the stereochemistry?
sir, but you didn't mention which chemistry.
No, no. What about the OH stereochemistry above the plane, below the plane? That's what I am asking. So if you use this Woodward reagent, in Woodward reagent, what you got? Actually, you got syn-diol. Okay, syn-dihydroxylation. So that means the stereochemistry of both the OH will be same. Both the OH will be same. You can see here, both the OH will be same page. Okay, same plane. So if you do this, here we are getting, you will get both the
Trans
OH like this, not transis. This is your syn dihydroxylation. In Woodward reagent you will get syn dihydroxylation, but if you use Prevost reagent, Prevost, that time you will get like this, anti.
and
Prevost you will get anti, okay, or trans. So when you are using Prevost, that time one OH will be above the plane and one OH will be below the plane. That is the only difference. So in Woodward dihydroxylation you will get syn dihydroxylation, but if I talk about Prevost reagent, that time you will get anti dihydroxylation. This is the only difference you have. Okay, clear?
yes, sir. Yes, sir.
Clear, right? Okay, so you're done with this dihydroxylation topic. Next we have, write down that cleavage of cleavage of carbon carbon double bond. Okay, cleavage of carbon carbon double bond. Okay, so suppose I have this. Okay, I have this. Here I am using osmium tetroxide, right? So you know what is the product? What will be the product if I use osmium tetroxide?
Then dihydroxylation.
Syn dihydroxylation.
Um,
So diol you will get OH and here also you will get OH. You can show above the
okay.
plane, below the plane, both are correct. Now the second reagent what we are using here, that is actually known as this reagent NaIO4, sodium iodate. Okay, sodium iodate. So if you use this, so what, sodium plus IO4 minus, so you can draw the structure like this: iodine, double bond O, here also you have double bond O, here double bond O, and here you have O minus. Okay, now what will happen? So OH, right? So OH has lone pair, it will attack on the iodine center. Okay, once it attacks on the iodine center, this bond will break. Okay, similarly this oxygen has also lone pair, so it will also attack on the iodine center. Okay, and what will happen? This bond will break. Okay, so oxygen has lone pairs, they are actually attacking on the vacant orbital of iodine. So what we are getting, so you are getting a thing like this. See what we are getting. So I have here oxygen, OH is there, so oxygen is donating electrons, so that means what, it will be positively charged. So this double bond O is breaking, right? So I am getting what here, O minus. This oxygen is becoming what, positively charged. Here I have double bond O, here also I have what, oxygen. Okay, hydrogen, this oxygen is positively charged. Okay, it is attaching with your iodine, and when oxygen attacks here, so oxygen is donating electrons, it will be positively charged, and this bond is breaking, so it will be what, negatively charged. And here already you have O minus. Now the next step will be what, O minus. So O minus will abstract this acidic proton. Once it abstracts the acidic proton, this oxygen is getting neutralized. Here also this O minus is abstracting the proton, and this oxygen is now becoming what, neutralized. Okay, so what I am getting basically, so you will have here oxygen. Okay, then you have here iodine, you have here also oxygen. Okay, now this O minus will convert to what, OH. Okay, here you will get double bond O minus, and this O minus is also abstracting proton, so it will also become what, OH. Okay, clear?
Yes, sir.
Now what will happen? Now see, this O minus is giving back its electrons, so what will happen, this bond will break, this bond will also break to here, and ultimately this bond is breaking. So what we are getting, so this sigma bond breaks, so that means you will get carbonyl compounds, or basically aldehyde compounds you are getting now. Okay, aldehyde compounds you are getting, and what is the side product you are getting? So you will get this double bond O, double bond O, OH, OH. Okay, done.
It,
So ultimately
uh,
what, yeah.
uh, yesterday someone asking that single bond, how the single bond will break that.
Ha.
I have a similar doubt also.
Here basically how the sigma bond is breaking, so you can see O minus is donating back its electrons. Okay, when it gives back its electrons here, automatically this bond has to break. Okay, automatically this bond has to break, because electrons are coming from this here, from this oxygen center, so it moves the electrons to here, this bond breaks, automatically this bond will break. Why? Because the antibonding orbital is there, so the electrons are coming to the corresponding antibonding orbital, and this sigma bond breaks. Okay, She was asking why the other single bond is breaking. Why she was not asking that. See, this double bond is this. Initially, you have here double bond. After dihydroxylation, you are getting single bond, but this double bond can easily break. Okay, what
Yes,
is
sir.
the reason why it is breaking? So this O minus is giving back its electron density to here. Now you can consider like that. Suppose this is your iodine oxygen bond, so the anti-bonding orbital will be present here. So basically this O minus is donating the electrons into its anti-bonding orbital, and when it is donating the electrons in the anti-bonding orbital, this sigma bond will automatically break. So if it breaks, so that means what? Electrons are coming to here, so that means this single bond has breaking now. Ultimately this single bond is also breaking. Okay, so it's a continuous process. It's not like a stepwise process. Electrons are flowing from here to here to here to here. Clear?
Yes, sir.
So basically you will get like this how to do. So initially you are getting diol. Okay, how to do? So if you have osmium tetroxide, you will stop here, but if they are giving you this sodium iodate, so that time you have to break the single bond in between the two OH, and you have to make it corresponding aldehyde. Okay, you have to make it corresponding aldehyde. Okay, aldehyde or ketone, whatever you are getting, you have to do this. So suppose I have this compound. Write down the product. Tell me easy question. Write down the product. What will be the product? Am I audible?
Yes, sir.
So what will be the product if you give here osmium tetroxide?
Still dihydroxylation happens there, first
Uh,
one. Here, second one is oxidative damage.
so syn dihydroxylation means what? You have to attach two OH.
Yes, sir. Two OH.
Okay, and when you are using sodium iodate, so initially you will get this. Okay, initially you
Same
will get
product.
syn dihydroxylation. Then you have to break this sigma bond. Okay, if you break this sigma bond, because in presence of sodium iodate this sigma bond will break, so what you will get? What you will get? You will get
C
here,
double bond.
yeah,
C double bond O C.
cyclohexanon, and this is what? This one will become this H C double bond OH, formaldehyde. Okay, you have only one carbon atom, so if you have only one carbon atom, you will get formaldehyde. Okay, Kaveri,
Yes,
clear?
sir.
Kaveri, clear?
Clear, sir.
Clear, right? Ask me any doubt, okay? Okay, next you have, this is very important. So this is your ozonolysis. Okay, I think all of you know what is ozonolysis. Okay, so basically here we will see we have two types of ozonolysis. Okay,
Oxidative and reductive.
reductive and oxidative. Oxidative and reductive. Now what are the reagents? So basically first of all I am writing for reductive. So here you will have ozone in presence of dimethyl sulfide Me2S. Okay, or you can use ozone in presence of zinc dust. Okay, or you can use ozone in presence of pph3. Okay, pph3, or someone can also use ozone in presence of zinc acetic acid. So these are the reagents basically we use for reductive ozonolysis. And when we are talking about oxidative ozonolysis, that times we will use some reagents like this. Suppose H2O2, hydrogen peroxide. Okay, or you can use ozone in presence of CrO3, chromium trioxide. Okay, or ozone in presence of KMnO4. So these are all oxidizing agent. So if you are using this reagent, hydrogen peroxide, chromium trioxide, KMnO4, that time it is your oxidative ozonolysis will happen. Okay, now the next thing, suppose you have alkene. Okay, so this alkene will convert to what? Alkene will convert to,
Aldehyde
yeah, aldehyde
or ketone.
or ketone when we are doing reductive
Reductive.
ozonolysis. Okay, reductive ozonolysis. But if you do oxidative ozonolysis, that time you will get ketone, and in presence of this oxidizing agents, the aldehyde will convert to what? The aldehyde will convert to what? Acid, carboxylic acid. Okay, yesterday I told you no, that aldehyde is unstable, so that
Yes.
can further oxidize to your carboxylic acid. So ketone plus acid you will get in your oxidative ozonolysis. So these are the two types of thing. In a reductive ozonolysis you will get carbonyl compounds only, but in oxidative ozonolysis you will get carboxylic acid plus ketone, because ketone cannot be oxidized, but aldehyde can be oxidized. Okay, write it down. Done.
Yes, sir.
Okay, now do some questions. So suppose you have this carbon carbon double bond, hydrogen hydrogen. Okay, here you have methyl, here also you have methyl, O3H2O2, and here I am using O3 in presence of Me2S. Write down the product. Kaveri, tell me what is the product for this O3H2O2?
First one, we are getting aldehyde, acetaldehyde, and aldehyde, sir.
Hmm?
Acetaldehyde.
Acetaldehyde, how you are getting acetaldehyde? How to do ozonolysis? So ozonolysis means you have to remove this double bond. Now attach one oxygen to this side and another oxygen to this side. So what I will get? I will get this. This is your formaldehyde, not acetaldehyde. Okay, acetaldehyde means CH3CH. So formaldehyde
Twice the chemistry.
plus what? Acetone. Acetone. Now this reagent is what? Oxidative or reductive?
Oxidative.
Oxidative. So
Oxidative.
oxidative. So formaldehyde will further oxidize to what?
Acid.
Formic acid.
Formic acid.
HCO2H. Okay. So this will be your final product. Formic acid plus acetone. Clear?
Yes, sir.
It will not stop in your aldehyde. If you are using oxidative ozonolysis, so that means the aldehyde will further oxidize to your carboxylic acid. Ketone will not oxidize. And if I talk about reductive ozonolysis, that time you will get this only. That time you will get
Formaldehyde plus
only
acetone.
formaldehyde plus acetone. That time you will get this formaldehyde plus acetone, but in oxidative ozonolysis the formaldehyde will further oxidize to the corresponding carboxylic acid. See how many carbon atoms are there? Only one carbon atom, so one carbon containing carboxylic acid you will get. If you have two carbon atoms, so two carbon containing carboxylic acid you will get. Clear?
Yes, sir.
This is a protecting group OTBDMS. Tell me what will be the product.
The terminal vinyl group will convert into acetaldehydes. Sorry, aldehydes.
Hmm. So this is what, oxidative or reductive?
Reductive.
Reductive. So you have to just break the double bond, then attach one oxygen to this side, one oxygen to this side. So what I am getting? I am getting this. So here you will get this double bond O. This is also aldehyde because nothing is there, so that means hydrogen is there. And here you have only one carbon atom, right? This side, right hand side, only you have one carbon atom. So that will be what? That will be your formaldehyde. Clear?
Yes, sir.
Clear?
So,
Okay. Just check what is the reagent they are giving, oxidative or reductive. If reductive, that time both side attach one oxygen. Okay, that's it. If oxidative, so your aldehyde will oxidize to your carboxylic acid. That's it. Okay. Suppose you have this. Now you have here O3 Me2S. Just break the double bond and then attach two oxygen to the two carbon atom. That's it. So what? First of all, O3Me2S is what? Reductive or oxidative? Check, I have written.
Reductive.
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 So you have to break this double bond. You have to break this double bond. Okay. Then attach one oxygen to this side and one oxygen to this side. So that means one oxygen with this carbon atom and one oxygen with this carbon atom. If you do that, what you will get? What you will get? So here you are getting double bond O, and already you have this methyl group. So place the methyl group CH3, and this side also you will get what? Double bond O. Nothing is there, so that means hydrogen is there. So that is your aldehyde, and this part is becoming ketone. If you use this O3CrO3, this is what? Reductive or oxidative?
Oxidative.
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 So that means what? Above part you will get ketone. Okay. Now this down part you don't write down aldehyde only. This part you have to write down like this, CO2H, because the CHO group will convert to what? CO2H. Clear?
Yes, sir.
Yes, sir.
Okay. Now this question do by yourself. Okay, fine. This question, tell me which double bond will be oxidized. You are using only one equivalent, okay? We are using only one equivalent.
Sir, ozone will react with the most electron rich double bond. That is
Hmm.
present
So
next to
ozone is
OCH.
basically what? Ozone is looking like what? Ozone molecule means this, na?
Yes, sir.
This is your ozone molecule, okay?
Ozone.
So basically ozone is basically your electron deficient.
Electron deficient.
Okay, why electron deficient? Because this oxygen is getting positively charged. So this ozone is actually electron deficient. So you have to check which double bond is electron rich. So if methyl
First one.
group is attaching, yeah, if methyl group is attaching, so that means what you have? You have inductive
Electron
effect
only
as
plus
well
A.
as hyperconjugation.
Plus A.
Okay, but you have
Plus
oxygen.
M.
Hmm. So plus M is present there. Okay, oxygen lone pair basically is in conjugation. If it is not in conjugation, that time it will be minus I. But if it is in conjugation, that time it will show you plus M effect or plus R effect, resonance. And we all know what is the stability order. Resonance greater than hyperconjugation greater than what? Inductive. So this OCH3, this actually becomes more electron rich center. Okay, this actually becomes more electron rich center. So you have to break this double bond only and then attach one oxygen to this carbon atom, one oxygen to this carbon atom. So what I will get, CH3 is there. Okay, here you have OCH3. Okay, now attach one oxygen, double bond, and with this carbon atom also you have to attach one oxygen, double bond. So this is your aldehyde, and this is which group? Which functional group, Kaveri? This one. This one is which functional group? Double bond O, OCH3.
It's ester.
Ester, right?
Ester group, sir.
Yeah, ester. Now next step, suppose I am treating this compound with sodium borohydride methanol. What will happen?
Ester is converted into
Alcohol.
Which one?
alcohol.
Which one will convert? one will convert, ester group or aldehyde?
Ester, sir.
Hmm?
Yes, sir.
Ester.
No, no. Check the notes, check
We
your
are doing
notes.
grading.
Check your notes. We have done sodium borohydride, lithium aluminum hydride. Check your notes. Which functional group will convert? Tell me. Check your notes. Sodium borohydride.
Aldehyde.
Aldehyde. So this CHO group will convert to what? CH2,
Alpha
CH2OH. Ester group will remain intact. Okay. Ester group will not change anything. So double bond OCH3. But if you use here lithium aluminum hydride, okay, in
Both
presence
are
of
present. Yes.
ether or THF, so that time both your ester and aldehyde will reduced. Okay, both your ester and aldehyde will reduce to the corresponding alcohol derivative. Is it clear?
Yes, sir.
Reagent chemistry you have to revise a lot, okay, otherwise you will forget one by one.
Yes.
Organic chemistry you have to revise, okay.
Yes.
See, we have not finished till yet reagent chemistry, but you have already forgotten that lithium aluminum hydride and sodium borohydride thing, okay. That should not happen actually. You have to revise it, okay. Hardly one class require for this reagent chemistry, not full one class, only half class. Then we are done with this reagent chemistry. Okay, so here you have O3 in presence of H2O2. Uh, also, so yeah, tell me what will happen. So first of all, tell me which ring is more electron rich.
Pyridine ring will be
Aromatic.
Benzene ring or pyridine ring? Which ring is more electron
pyridine.
rich? Huh? Benzene ring or pyridine ring? Which ring is more electron rich?
But it is also aromatic.
Benzene rings, sir.
Benzene rings.
Nitrogen is not in conjugation with this group.
So your benzene ring will
So
be more electron rich because nitrogen lone pair is not in conjugation.
But it
Same
is
example.
aromatic.
Both are aromatic. Both are aromatic.
Uh,
Both are aromatic. But yesterday we have done this kind of example
uh,
also, na? Here also I have told that what? Here nitrogen lone pair is not in conjugation. Okay, this
the
nitrogen
voice
lone.
is clicking, sir.
Now it's fine.
Yeah.
Am I audible?
Yes, sir. You are audible, sir.
Okay. Okay, so here what is happening, this nitrogen lone pair is not in conjugation. Okay, so that's why it is showing minus I effect, and that's why this pyridine ring is becoming electron deficient. Benzene ring is more electron rich. So here also the same thing. Here also the same thing. Benzene ring is more electron rich, so, and this ozone is basically your electron deficient. Ozone is basically is your electron deficient and this is your electron rich ring. So what will happen, the ozonolysis will happen here. So you can break this bond, so you have to attach one oxygen here, one oxygen here, and you have to break this bond, so you have to attach one oxygen here, one oxygen here. So you will get a molecule like this, double bond O, double bond O, plus what you are getting, now you are getting this Okay, so here you are attaching oxygen, so that means it will be double bond O hydrogen, and this side also you are attaching oxygen, so that means double bond O hydrogen. So what, this is aldehyde. Now tell me, this is what, this is your oxidative or reductive? Oxidative.
Oxidative.
So if you use oxidative, so that times the aldehyde will further oxidize to what, carboxylic acid. Okay, the aldehyde group will further oxidize to carboxylic acid, so that will be your product. Okay,
Sir, again your voice is breaking, sir.
voice is breaking.
Yes, sir.
Okay, just a minute, just a minute. Yeah, now am I audible?
Yes, sir.
Audible, right?
Yes, sir. Yes.
Okay, fine.
Sir,
Okay, fine. So now the next reagent we have, this is your PCC. So PCC means what? PCC means, write down, pyridinium. Okay, just a minute. Yeah, pyridinium chlorochromate. Pyridinium chlorochromate. Okay. So PCC means what? Pyridinium chlorochromate. Okay. So first of all, what is PCC? So if you react pyridine, if you mix pyridine with CrO3, chromium trioxide, with HCl, okay, with HCl, so that time you will get this pyridinium chlorochromate. How it looks like? So pyridine structure, you know, this is your pyridine. If pyridine abstracts one proton from this HCl molecule, so it will look like what? It will look like this. Okay, Cl minus dot CrO3. So this is basically your pyridinium chlorochromate. Now what is the conversion will happen by this reagent? So write down that alcohols will convert to carbonyl compounds. Alcohols will convert to carbonyl compounds. Okay, now the second point, what it is doing? Controlled oxidation. Controlled oxidation, not full oxidation. Okay, full oxidation means what? Alcohol will stop in your carboxylic acid, but here PCC is a mild oxidizing agent. Okay, keep in mind, this is a mild oxidizing agent. So mild oxidizing agent means what? It will stop in this carbonyl compounds, aldehyde and ketone. So if you have primary alcohol, that will oxidize to your aldehyde. If you have secondary alcohol, so that will oxidize to what? Ketone. If you have tertiary alcohol, so no reaction will happen. If you have tertiary alcohol, so no reaction will take place. Okay, and another thing is what? This is your 3 degree allylic alcohol. 3 degree allylic alcohol, so that time we will get ketone, and this is basically a pericyclic reaction. This is also known as your 3,3 sigma-tropic reaction. So that are the points you have to remember, all of you. So if you have primary alcohol, you will get aldehyde. If you have secondary alcohol, you will get ketone. If you have tertiary alcohol, normal tertiary alcohol, that time no reaction. But if you have tertiary allylic alcohol, that time 3,3 sigma-tropic reaction will take place and you will get your ketone compound. Is it clear? Now my voice is clear?
Yes.
Okay, fine. So suppose you have this compound. Suppose you have this compound, okay, cyclohexanol. If I treat this compound with PCC, what I will get? So it's a what? Secondary alcohol. So you will get ketone compound, cyclohexanone. Okay, cyclohexanone. So if you have primary alcohol, you will get aldehyde. If you have secondary alcohol, you will get ketone. If you have tertiary alcohol, no reaction, and tertiary allylic alcohol, you will get ketone by 3,3 sigma-tropic reaction. Now what is the mechanism of this kind of reaction? So suppose you have any alcohol. So I am showing for a primary alcohol. So suppose this is a primary alcohol you have. Okay, these questions actually they asked me in Nizer Kolkata interview, that for they are asking for allylic alcohol. Okay, so mechanisms are important. Okay, for organic chemistry mechanisms are important. So what you have? Chromium trioxide. So chromium trioxide means what? Like this, chromium double bond O, double bond O, double bond O. So what will happen? Oxygen lone pair will attack on the chromium center. This double bond is breaking. So what I am getting? What I am getting? So oxygen is there, hydrogen is also there. Okay, chromium is attaching with this. Here you have, I am writing like this, this one you will get O minus. Here you have double bond O, here also you have double bond O. Here oxygen is donating the electron, so it will be what? Positively charged. Now this O minus will abstract the proton from here. Once the O minus abstracting the proton from here, what you will get? You will get this oxygen, and here you are getting what? Chromium. Here you have OH. Okay, then you have here double bond O, double bond O. Clear?
Yes, sir.
Clear? Okay. Now see, here you have one hydrogen. So same thing I am writing like this. Okay, same compound I am writing in a different style. So now I am keeping double bond O here. Okay, and OH here, double bond O here, and here you have proton, right? So oxygen has basically lone pairs. Okay, this oxygen has lone pair. So what will happen? Oxygen will abstract the proton, this bond will break to here, ultimately this oxygen chromium bond will also break. So what I am getting, see, this bond moves to here, right? So you will get a thing like this, double bond O. Okay, plus what you are getting, what is the byproduct? Chromium. This double bond O is abstracting the proton, so it is now becoming OH, OH, double bond O. Clear? What you are getting here? Aldehyde, na? So if you have primary alcohol, what you are getting as your product? Aldehyde. Clear? Mechanism is clear?
Yes.
Kaveri, clear?
Yes, sir.
Clear, right? Okay. Okay, turn off the mic, okay? Turn off the mic. Thank you. Now suppose you have this PCC. Okay, so again see, this is what this OH is attaching with how many carbon centers? 1 2 3, 1 2 3. So this is what, this is a tertiary alcohol. So if you have tertiary alcohol and you are treating this tertiary alcohol with PCC, so that time what you will get? You will get no reaction. Okay, no reaction will happen. Okay, if you have tertiary alcohol and you are doing reaction with PCC, no reaction will take place there. Okay, but suppose I have this. Okay, do you know what is allylic alcohol?
This carbon connected to carbon carbon double daily carbon.
Allylic alcohol means what? So you have a double bond and next carbon
Connect.
you have OH, right? CH2OH, this kind of thing, double bond. This is actually allylic alcohol. So OH is attaching to the next carbon of this carbon carbon double bond. Here also it is same, OH is attaching to the next carbon of your what? Carbon carbon double bond. So this is what? This is a allylic alcohol. But if you see, this OH is attaching to how many carbon centers? 1 2 3 3.
So,
So yeah, any doubt?
not so clear.
So this is what? This is your 3-degree allylic alcohol. 3-degree allylic alcohol. Okay, now you have to show the mechanism. I already mentioned what will happen here. Pericyclic reaction will happen, right? So see how it is happening. So first of all it will do normal mechanism. Okay, normal mechanism here. So oxygen has lone pair, so OH is donating the lone pairs to the chromium center. This double bond O is breaking. Okay, so what I am getting, so here I have CH3, here what I have, oxygen is donating electrons, right? So it will be what? Oxygen is donating electrons, so it will be positively charged, and this double bond O you are getting negative charge, right? Now O minus is abstracting this proton from here, so this bond again it breaks. Okay, oxygen is getting neutralized. So what I am getting? What I am getting? CH3. Here you have oxygen. Now you have chromium. Okay, chromium is there. Okay, now here I am getting what? OH. Then what I have? Double bond O. Here also I have double bond O. Okay, this is the thing. Now I already mentioned here that if you have 3-degree allylic alcohol, you will get ketone by what? 3,3 sigmatropic reaction. Now see how to do this 3,3 sigmatropic reaction. So now just mention here what will happen. 3 3. Okay, write down 3,3 sigmatropic 3,3 sigmatropic reaction. Now how to mention actually? So see, mark this oxygen as 1, chromium as 2, and this oxygen as your 3. Okay, now see, this carbon atom, this tertiary carbon is 1, this is 2, and this is 3. So 1 2 3. This is also what? 1 2 3. Now oxygen has lone pairs, all of you know that oxygen has lone pair. So what will happen? Oxygen will attack this 3 position. So from 3 position to 3 position it will attack. When oxygen is donating the lone pairs to this carbon atom, what will happen? This double bond will shift to here. Okay, this bond will break. Clear?
Yes, sir.
Clear?
Yes, sir.
So here you will get a transition state like that. Okay, So this transition state is basically 6-member transition state you will get. In interview they ask like why this is happening. So this is basically pericyclic concept, but yeah, still you have to say that this we are getting 6-member transition state. That's why this 3,3 sigmatropic reaction is a stable pathway or stable process. So now this double bond is shifting to here, here, and ultimately here. So see, 1, 2, 3, 4, 5, 6. Okay, this is the transition state. Okay, this is the transition state. So what is happening? See, this double bond is shifting to here, right? So that's why I have shown like dotted. Okay, so that means this bond is breaking and here a bond is forming, so like that. So that's why I am showing in dotted. Now this bond is breaking this carbon oxygen bond, that's why I have shown like this. Okay, okay, and here already you have a sigma bond, so give the sigma bond, and this bond is shifting to here, so this bond forms here, already you have a single bond, and here also when the oxygen donates, so that means this bond will break. So ultimately what you will get, we'll get a compound like this. What you are getting? What you are getting? Tell me. See, the double bond shifts to here, this position, right?
Yes, sir.
This double bond shifts to this position. So first of all, write down here, double bond shifts to this position. And now see, this oxygen is now attaching with this carbon center, 3 3. Oxygen is now attaching to this center. So write it down. Okay, so here I have oxygen, then you have chromium. Okay, double bond O, double bond O, OH. Okay, you can see what you are getting. So this double bond O and this is double bond O, and you have one OH. Okay, this bond breaks to here, so this becomes double bond O. You have already one double bond O and OH is there, so you are getting this compound. Okay, now the next step is what? You have hydrogen here, so this hydrogen will break, this hydrogen will leave from here. So basically you can think like this, that hydrogen, this bond is coming to here and this whole group is a good leaving group, so that will leave from here. So ultimately what you are getting, double bond O methyl, this is known as your chromate ester. Okay, or chromate ester derivative. So basically what is happening, hydrogen is donating the electron density to this and this group leaves. Or you can think like that water is there, because reaction you will have water is abstracting the proton from here, so this bond breaks to here and this is a good leaving group which is leaving from here. Okay, so ultimately what you are getting, you are getting ketone compound. Okay,
So,
clear? In this mechanism you have any doubt? Tell me. In this mechanism you have any doubt? Any doubt?
Clear, sir.
Clear? All of you clear, right? Okay,
so
fine. If any doubt, ask me. Okay. Okay. Suppose you have this cyclohexanon allylic. Okay. Now here I am using MELI. Tell me what will happen. What will happen? Alkyl lithium we have done, na? Alkyl lithium.
So
So what it will do? One to
Me
attack or
minus will at Me minus will attack the double bonds.
double bond? One to attack or one for attack? What it does? Alkyl lithium. This is what, hard or soft? Hmm. Turn over the pages. Check what it is doing.
Hard, sir. 1 to attack, sir.
Hmm. Alkyl lithium is basically hard reagent. Okay. This is
Yes.
not
Yes, sir.
soft. So this is 1, 2, 3, 4. So 1 to attack. If you have soft reagent, that time it will attack here. 1 for attack. But if you have a hard reagent, that time it will do 1 to attack. So it will attack on the carbonyl carbon. What you will get? So you have here Me and it is becoming
OH.
O minus. Yeah, so it is becoming OH. Okay. So you are getting now what? Tertiary allylic alcohol. If you give here PCC, you know the mechanism now. Now see how to do. So basically, first of all, you write down the compound what you have. Now shift the double bond to this center where you have the methyl group or tertiary group. Shift the double bond to here. Okay, shift the double bond to here, and this OH oxygen will come to here from where it is actually migrating. So here just write down double bond O. You will get your product. Okay, shift the double bond to this tertiary center and OH will come, oxygen will come to this position from where actually the double bond was. Okay, so after 3,3 sigma tropic reaction you will get this product. Check. Clear? Clear?
Yes, sir.
Okay, suppose you have this. So this is also your 3-degree allylic alcohol. Okay, this is also your 3-degree allylic alcohol. If I give here PCC, so write down no reaction. So why here the reaction is not happening? Because this methyl group is actually blocking this position. Okay, so OH cannot shift to this position. Why? Because this position is already occupied by this methyl group. That's why no reaction. So here if your this position is blocked by a alkyl group, so that time 3-degree allylic alcohol will also react as a 3-degree alcohol. So that time no reaction. Okay, clear?
Yes.
Sir.
Okay, my voice is breaking.
No, sir. Clear, sir.
Clear, right? Okay, fine. So this is the molecule you have. Here I am giving PCC. Tell me what will be the product. Do it. Which system this is?
Tertiary allylic alcohol, sir.
Tertiary allylic alcohol. So what will happen? Do it.
Sigma tropic. 3 sigma tropic action.
So what will happen? This double bond will shift to here. This oxygen will move to here,
Yes.
right? So double bond is shifting to here. This oxygen is shifting to here. So double bond. Clear? How to write down in a like,
Yes.
okay, without mechanism how to check?
Yes, sir.
Hmm. Clear, Kaveri? Clear?
Yes, sir.
Clear, right? Okay, fine. Now next question. Next question. Do it, do it. What will happen? So basically they are using like this PCC in presence of sodium acetate or ammonium chloride water or NaH2PO4. This is actually known as your buffer solution. Buffer solution. So what will happen? This is what? Which alcohol it is?
Secondary.
Secondary alcohol. So in presence of PCC, secondary alcohol will convert to what?
Ketone.
Ketone. So
Me too.
just make it, yeah, just make it double bond O. That's it. Just make it double bond O. That's it. The secondary alcohol will convert to your what? It will convert to your ketone compound. Okay, done.
Yes, sir.
That's it.
Okay, now the same compound, but the reagent is different here. So now here I am giving PCC in presence of CH2Cl2. CH2Cl2 means DCM, okay, and you have HCl. So that time HCl, if I am using HCl, so that means it's a acidic condition. So first of all, do this in presence of PCC. What it will convert? The secondary alcohol will convert to your ketone compound. First of all, there is no change. This thing you are getting. Okay, now in presence of HCl, what will happen? This double bond O will be protonated. This oxygen is abstracting the proton, so this double bond O is getting protonated. Okay, so you have positive charge here. Here I have methyl group, and here I have OBN. Now when it is getting protonated, that time what happens? Now there is a chance of carbocation formation. So see, if this double bond is breaking and it is attacking on this carbon center, so that time this double bond will break and oxygen will get neutralized. And what is forming? A 5-membered ring is forming. 5-membered ring is forming. So you are getting like this 5-membered ring. This position you are getting OH, and this isopropyl type. So carbocation is basically forming here. Now you can ask me, sir, why not 6-membered ring is forming? Because 6-membered ring formation is also possible. If I break the double bond in this direction and it is attacking in this carbon atom, then there is a possibility of 6-membered ring formation, right? So why we are not doing that? If you do this 6-membered ring formation, so that time you will have your OH, and yeah, you will get the structure like this. So these are the two possibilities you have here from this compound. If your double bond is getting protonated, so this double bond, the adjacent double bond, can now break in two directions. One direction you will get this 5-membered ring with this tertiary carbocation, and the other you are getting 6-membered ring with a secondary carbocation. So here why it is not forming? Because this carbocation is more stable. This carbocation is more stable. It's a 3-degree carbocation, it is more stable. Okay, and this is less stable, so that's why it is not forming. Okay, and the next step will be what? Because we are doing in presence of acidic condition, so that means some amount of water is already present there. Okay, so water will abstract the proton, and ultimately you will get this elimination reactions is happening. So what I am getting, double bond, this, here I have methyl, and here I have OBN, here I have OH. Okay, clear? Any doubt?
Yes.
Clear? Any doubt? PCC reagent, any doubt you have? Both of you clear?
Yes.
Okay, fine. Now write down the next question. Which reaction this is? Zinc copper in presence of CH2I2.
Simon's
Simon-Smith reaction. Good. So if you have Simon-Smith reaction, what will be the product?
cyclopropane.
Cyclopropane ring. Correct. So 3-membered ring will form here. 3-membered ring will form here. Carbene formation, first of all, carbene formation will be there, and carbene will add with the double bond. So you are getting what? Cyclopropane ring formation. Simon-Smith reaction. Very good. Now next we have given PCC, but only one equivalent. So what will happen? This is what? This is your primary alcohol, right? So this primary alcohol will oxidize to what? Aldehyde. So this is
Aldehyde.
a double bond O hydrogen, and this side you have what? CH2OH. So now what is possible? Now what will happen? Now oxygen will attack on this carbonyl carbon, and this bond is breaking. Okay, so what we are getting? So I have a 3-membered ring, and here I am getting 1 2 3 5-membered ring we are getting, and this double bond O is breaking, so ultimately you will get OH. Okay, but already we are using PCC, so in presence of PCC what will happen? In presence of PCC, this is what? Secondary alcohol, na? So secondary alcohol will convert to ketone. don't stop the reaction here. Don't, in options they will give you both the product, this product also, this product also, so don't mark this product because you have a secondary alcohol. So in presence of PCC, the secondary alcohol will further oxidize to your ketone compound. Okay, it will not stop there. Clear? So first reaction is your Simon-Smith reaction. After that we are treating this compound with PCC. So in presence of PCC, the primary alcohol is oxidized to aldehyde. Now intramolecular reaction is happening. So because you have already intramolecular nucleophile is present there, so it is attacking, you are getting OH. Again in presence of PCC, the OH will oxidize to your corresponding ketone compound. Clear?
Yes, sir. Yes.
Any doubt from PCC?
Yes, sir.
No doubt, right?
Yes.
Okay, fine. So next you have PDC. So what is PDC? So PDC is known as, write down, pyridinium dichromate. Pyridinium dichromate. So what is pyridinium dichromate? So write down pyridine plus CrO3 chromium trioxide plus acetone. Pyridine plus chromium trioxide plus acetone. What it will do? So again write down what? Oxidation of alcohol. Oxidation of alcohol. Okay, this is the first point, oxidation of alcohol. And second point is what? Solvent dependent. Okay, solvent dependent in case of primary alcohol. Solvent dependent in case of primary alcohol. Okay, so oxidation of alcohol, and second thing is what? Solvent dependent in case of primary alcohol. So basically this is something different. So if you have primary alcohol, now suppose we are using PDC, not PCC, we are using PDC. So if you have DCM, if you are using DCM as a solvent, so that time you will get aldehyde. Okay, if you are using DMF as a solvent, so you will get carboxylic acid. If you are using alcohol as a solvent, so you will get ester as a product. And if you are using liquid ammonia as a solvent, so you will get amide as a product. Okay, so basically this primary alcohol depends on the solvent. Okay, but if you have secondary alcohol, that time directly you will get ketone compound. Suppose I have this primary alcohol. Suppose here I am using PDC in presence of what? DCM. So what we will get in DCM? Aldehyde. So make it aldehyde, double bond O, hydrogen. Suppose next I am using PDC in presence of what? DMF. So if you use DMF, so the CH2OH will convert to what? CO2H. Okay, so that time you will get corresponding carboxylic acid. If you use PDC in presence of alcohol, so suppose PDC in presence of methanol. Okay, methanol, so that time you will get ester. So double bond O, what is the methanol? So alcohol, OMe. Okay, if you have liquid ammonia, So that time I will get double bond O NH2 amide. So these are the things you will get. PDC in presence of liquid ammonia. PDC in presence of liquid ammonia, you will get corresponding amide derivative. Clear? Clear? Done?
Done, sir.
Clear, sir.
Clear, right? And if you have secondary alcohol like this, suppose secondary alcohol that is not solvent dependent. So in case of secondary alcohol, if you are using PDC, so definitely you will get your this product, ketone product. Okay, if you have secondary alcohol, so that time it does not depend on the solvent, you will get directly ketone product. Okay, next we have Collins reagent. Okay, Collins reagent. So what is Collins reagent? So it is also pyridine reagent, pyridine plus chromium trioxide plus DCM. So here we are not using acetone, here we are using what? DCM. Okay, so this Collins reagent, if you have primary alcohol, so this primary alcohol will oxidize to aldehyde. Okay, if you have secondary alcohol, so that will oxidize into ketone. Okay, fine. So suppose I have this primary alcohol R CH2OH. Okay, here I am using this pyridine plus what? Chromium trioxide in presence of DCM. What you will get? You will get RCHO, benzaldehyde. Aldehyde, primary alcohol will oxidize to what? Aldehyde. Suppose you have here benzene ring. Okay, and here you are giving this CH2OH. Okay, same reagent you are using, pyridine plus chromium trioxide in presence of DCM. So here also it is your primary alcohol, right? So in presence of primary alcohol you will get what? Aldehyde, CHO. Clear? Clear?
Yes, sir.
Now solve one question. So suppose you have this. Okay. Tell me what will happen. So this is basically what? What is the reactant you have here? This is your 1,3-diol. Okay, 1,3-diol. 1,3-diol. What is the reagent you are using here? Acetaldehyde in presence of H plus, right? So acetaldehyde CH3 C double bond O hydrogen. In presence of H plus, what will happen? It will be protonated, right? MECHOH plus, in presence of H plus, what will happen? The reagent will be protonated. And once the reagent is getting protonated, what is happening? The electrophilicity of this carbon center is increasing. Okay, if this oxygen is becoming positively charged, so that means basically this carbon center is becoming more electrophilic in nature. Okay, so basically this is a protecting reagent, huh? If you have this kind of 1,3 diol and you are using some aldehyde in presence of H plus, so this is a protecting reagent. So this reagent you have to write down here. So suppose I have CH3 carbon hydrogen, initially you have double bond O, now it's getting protonated, so you are getting this positively charged. Okay, now what will happen? This OH has basically lone pairs, right? So this OH will attack on this carbonyl carbon and this oxygen is getting neutralized. So what I am getting? OH is there. So here also I have oxygen. Oxygen now attack this carbon center. Here you have methyl. Here you have hydrogen, OH. Okay, here you have CH3. This, 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 this. Here you have OH. Now also you have OH here, another OH. So this oxygen was also lone pair. So this oxygen is now attacking on this carbon center and this OH is releasing, leaving. Okay, leaving from here. So what ultimately you are getting? Oxygen, oxygen. Now see what is happening. So basically this 1,3 diol, this 2 OH is now protected. Okay, this protection is known as actually acetal protection. Okay, acetal protection. Acetal protection means what? Ether bond is forming. Ether means what? This kind of bond, na? Carbon oxygen carbon, carbon oxygen carbon. So this is your acetal protection. Okay, so basically what we are doing, we are protected this 1,3 diol, okay, by this reagent. Clear? So this OH is now keeping free, right? Okay, now you can ask me, sir, why this OH is not reacting? So basically you need this kind of syn relationship, huh? This kind of syn relationship you need to do react, like here both the OH is reacting one by one, right? But this OH is present in the opposite side, so it cannot react. Okay, fine. Now can you tell me, if I use here this reagent, what? Pyridine plus chromium trioxide in presence of DCM, what will happen? Hmm? This is what? This is your secondary alcohol, right?
Yes, sir.
So basically the secondary alcohol will oxidize to what? Ketone. Okay, the secondary alcohol will oxidize to ketone. Okay, clear? Very clear?
Yes, sir.
Any doubt? This is your protection, huh? This is your protection step. You can write down, this is your protection. Protection of 1,3 diol, and this is what? This is your acetal. Acetal protection. Acetal protection. Done.
Done.
Sir.
Hmm. Okay, next we have Jones reagent. Okay, Jones reagent. So what is Jones reagent? Write down again: chromium trioxide plus acetone plus H2SO4, sulfuric acid. Chromium trioxide plus acetone plus what? Sulfuric acid. Okay, so basically in Jones reagent you will get complete oxidation. Complete oxidation. Here no, this is not a mild reducing agent. Why? Because you are using H2SO4. H2SO4 is a concentrated acid. Okay, so when you are using concentrated acid, so that time if you have primary alcohol, so that will give you carboxylic acid, not aldehyde. Okay, if you have secondary alcohol, that will give you ketone, because ketone cannot be further oxidized, but aldehyde will oxidize to your carboxylic acid. Okay, so if I have primary alcohol RCH2OH in presence of this Jones reagent, okay, what you will get? You will get carboxylic acid derivative RCO2H. What is Jones reagent? CrO3 plus acetone plus what? H2SO4. Okay, if you have secondary alcohol, that time it will give you what? Ketone compound. Okay, but ketone cannot be further oxidized. Fine.
Yes, sir.
Done. Now do this question. Tell me, what will be the product? Hmm? Ketone, right? Ketone. Fine. Any doubt?
No, sir.
No, right? Okay, now next write down. This is the last reagent for today. Okay, we will not continue after that. Okay, Swan oxidation, but this is a very important reaction. Okay, very important reagent. Swan oxidation. Okay, so first of all write down the reagent. What are the reagent here? So COCl whole 2. So what is the name of this reagent? Oxalyl chloride. Oxalyl chloride. COCl whole 2. Oxalyl chloride. Plus what? Plus you have DMSO, dimethyl sulfoxide. Okay, plus you have triethylamine. This is what? Triethylamine is acting as a base. Okay, so these are the reagents you have to use: oxalyl chloride, DMSO, dimethyl sulfoxide, and triethylamine. This is a base. Now write down that in presence of base, what will happen? In presence of base, oxidation will happen. In presence of base, oxidation will take place. and in absence of base, what will happen? In absence of base, substitution will take place. So in presence of base, oxidation will take place. In absence of base, substitution will take place. Clear? Clear?
Yes.
So I am giving you a simple mechanism, not mechanism. Suppose you have this primary alcohol, okay. So if they have written like this, COCl whole to DMSO, okay, triethylamine minus 78 degrees centigrade. So what will be the product?
Aldehyde, sir.
Aldehyde, RCHO. Okay, if I give this reagent COCl whole 2 in presence of DMSO, that time what will be the product?
RCOCl.
Substitution reaction will take place. So basically Cl minus will attack, okay,
Yes.
and OH will leave. So you will get this,
Substitution.
yeah, RCH2Cl. So in absence of base you are getting substitution. In presence of base
Sir,
you are
your
getting.
voice is breaking.
Now am I audible?
Yes, sir.
Yes, sir.
You just turn off the mic, okay. I think that's why it's not clearly audible. Okay, now it's fine na. So in presence of this base, what is happening? You are getting this aldehyde. In absence of base, what I am getting? In absence of base, I am getting this substitution reaction. Okay, now I am coming to the mechanism part. Okay, so first of all I have showing one by one. So the dimethyl sulfoxide. So dimethyl sulfoxide is basically like this: sulfur oxygen double bond, you have CH3. So this thing we will not write down like that, we will write down like this: oxygen and sulfur. Oxygen is more electronegative than sulfur, so oxygen will be negatively charged, and sulfur will be positively charged. Oxygen is negatively charged and sulfur will be positively charged. Now if I react this DMSO, this is what, this is your DMSO, dimethyl sulfoxide. I am reacting this compound now with oxalyl chloride. So what is oxalyl chloride? C double bond O Cl. Here also you have C double bond O Cl. So what will happen? O minus is attacking on this carbonyl carbon. This bond is breaking. Again this bond is coming and chlorine is leaving from here. Okay. So what I am getting? CH3 sulfur CH3. Okay. Now here you have oxygen. Then what I have? C double bond O Cl. But this positive charge on sulfur, that is left, right? Okay, now the next thing is what? So see, you are getting this. Now what will happen? Now this oxygen sulfur bond will break from here. So basically what gas is releasing from here?
SO2.
CO2. This is what? This is your carbon dioxide. So CO2 is releasing from here, carbon monoxide is releasing from here, and also chloride is leaving from here. Okay, so write down here minus CO2, minus CO, and minus Cl. Okay, carbon dioxide and carbon monoxide is leaving from here and chloride is leaving. Now basically when chloride is leaving, so Cl minus ultimately is leaving, that is fine, but Cl minus will attack on this sulfur center. Okay, so ultimately what I will get this kind of thing: CH3 sulfur CH3, you have chlorine here and sulfur will have a positive charge. Okay, don't think that it will be neutralized, because when it is leaving from here, so that time another positive charge is generating on this sulfur center. So Cl minus is attacking on one positive charge, but one positive charge left. So that's why still the positive charge is present on your sulfur center. Okay, fine. Now the alcohol comes into role. Now what is the alcohol you have? RCH2OH, primary alcohol we have. So just write down the primary alcohol here. Okay, now plus what I have, sulfur, chlorine, CH3, CH3, and this sulfur has actually positive charge. So this oxygen is attacking on the sulfur center, chlorine is leaving from here. Okay, chlorine is leaving from here. So what I am getting, R CH2, here you have oxygen, sulfur, CH3, CH3, you are getting positive charge here. Okay, chlorine is leaving from here, you are getting. Now what you have triethylamine, right? Et3N. Triethylamine is what? It's a base, right? It's a base. So base will abstract proton, acidic proton. Which one is acidic proton? See, this CH3. Okay, this is already, you have acidic proton, so you have here CH2 hydrogen. So again triethylamine is abstracting one proton from here. So what I will get, so oxygen is there, you are getting sulfur. Okay, I am showing this CH2 as CH3, and this CH3 I am showing as CH2 minus, so it will be easy for me to show the next step. Same thing, this CH3 is also acidic, this CH3, both are symmetrical systems, so it can abstract proton from any one of this methyl group. So suppose it is abstracting methyl from here, so it is becoming CH2 minus. You have here proton, so what will happen, this CH2 minus will abstract the proton from here, this bond breaks, and ultimately this bond will break and sulfur will get neutralized now. So what we are getting, R double bond O, you have here hydrogen, and what is the byproduct we are getting, sulfur, CH3, dimethyl sulfide. Clear?
Yes, sir.
So what is the mechanism? First of all, O minus is attacking on this carbonyl carbon, you are getting this. Then CO2, carbon monoxide and chloride is leaving from here. So then Cl minus is attacking on this sulfur center, you are getting this. Then what is happening, alcohol, oxygen has lone pair, so it is attacking on the sulfur center, chlorine is leaving from here. Then we are using the base. Now write down, this is basically in presence of base. In presence of base, this reaction is happening in presence of base. Okay, so this is the intermediate we have, this is the intermediate I am marking here, this is the intermediate we have. Okay, in presence of base, what is happening, base is abstracting the proton from the methyl group. Now we will see in absence of base what will happen. So same intermediate you have, RCH2, oxygen, sulfur, CH3, positive charge. So see, this you have this Cl minus is already available in the solution, right? Cl minus is already available in the solution, so Cl minus will attack from the back side and this bond breaks. So what I am getting, we are getting R CH2 Cl plus what, we are getting sulfur double bond O methyl. So this is what, in absence of base. So in absence of base, substitution reaction is happening. In presence of base, oxidation reaction is happening. Clear?
Yes, sir.
Clear?
Yes, sir.
And this intermediate has a name. So write down, this has a name, this alkoxy sulfonium salt. Okay. This intermediate has a name, alkoxy sulfonium salt. This intermediate and this intermediate is same, so this is known as your alkoxy sulfonium salt. Done?
Done, sir.
Okay. Now suppose next you have this RC double bond to NH2. Okay. Now here also I am giving the same reaction, COCl oxalyl chloride in presence of DMSO. Okay, in presence of base. So I am showing you. So by this reagent, by this oxalyl chloride, DMSO and base, what actually generating? What reagent is actually generating? This reagent, na? This intermediate is generating, na?
Sir.
Yes, sir.
This intermediate, you can see here, this intermediate is generating by the mixture of this reagent DMSO and oxalyl chloride. So what will happen? So nitrogen has a lone pair, so this nitrogen lone pair is what? Is in conjugation with this C double bond O. So ultimately this O minus will attack on the sulfur center and chlorine is leaving from here. So what I am getting? So I can draw like this, RC. So here you will get double bond. Okay, in you can show NH directly or you can show NH2 plus, no matters. And here you will get oxygen. Oxygen is attaching with what? Sulfur, and you have two methyl groups here. See, if you see here NH2 plus, that time okay, fine, no need to worry. So ultimately you will get double bond NH, sulfur is getting positive charge. Okay, now next step, we are treating this compound with base, right? So you can see this is what? Acidic proton. Which proton is attached to nitrogen? That is your acidic proton. So what you will get? Double bond N. You will get a negative charge here. You have oxygen, sulfur, and you have two methyl group. Sulfur is getting what? Positive charge. These protons are also acidic. You can show like this. Okay, you can show like this. CH2 minus. Okay, but in the very next step, CH2 minus will abstract the proton from here because it is your sp2 hybridized. Okay, it is your sp2 hybrid, so you can show anything, but both are correct. Okay, so basically the proton will be abstracted from the nitrogen center. You will get N minus, and when it is abstracting, so what will happen? See, N minus will back its negative charge to here. This bond will break. So what we are getting? We are getting R C triple bond N plus what? DMSO is back. You are getting back DMSO reagent. Clear? Clear. So if you have
Yes.
amide and you are using this Swan oxidation, so you will get this nitrile compound. Okay. Done. Any doubt? Any doubt?
Done, sir.
Any doubt?
No, sir. Clear, sir.
No, right? Okay, fine. So that's it for today. Okay. I think, yeah, only two reagent left, immuno2 and fatty Jones reagent, that we will do in the next class. Okay, half an hour it will take. Okay, fine. Okay, bye. Thank you.
Thanks so much.
Thank you so
Bye.
much. Yeah,
Thank you.
bye. Yeah, bye. Thank you.